So I'm Nicola Montinaro. I present some results of a paper we published with University of Cambridge, and I'm going to talk about mechanical property of carbon nanotubes fiber. So the outline of this presentation, we will start with the definition of carbon nanotubes yarn, so the fiber. Then we will describe the finite element analysis model. We will discuss the results of the simple model, and again, after that, we will discuss the results for the more realistic model. And then we will conclude. Okay, what are the carbon nanotube fiber? So all we know what are the carbon nanotubes. They are pretty stiff and strong. So the bundle of nanotubes are a very common arrangement of nanotubes because they are pretty sticky. So this bundle of nanotube is mainly the basic component of our fiber. When we condense this bundle, we will obtain the fiber we talk, and condensing again the fiber, we will obtain this row that are a sort of useful material for fabric or high performance material in general. So having a look close to with the scanning electron microscopy, that is a magnification of the network we can find inside the fiber. And this is a high magnification. The network of nanotubes is pretty complicated, but we can having a look is pretty well aligned. That is a good thing. And of course, CNT fiber are made of well-aligned bundle of a carbon nanotube. Usually the bundle are arranged in group of 50, and they have an incredible length over diameter aspect ratio. What we are going to do? We are going to model a tensile test of a carbon nanotube fiber in order to understand the origin of the mechanical behavior. Why the origin? Because this kind of material have a very particular behavior, because the interface between bundle is ruled not by Coulombian friction. So if I apply a normal pressure, I will not obtain more shear stress. I will obtain always the van der Waals friction. So the material is pretty anisotropic, and it's pretty particular. So we started modeling with a 3D model here. The basic element I told you is this kind of hexagonal cell that represents the bundle of nanotube. This is the hexagonal pattern that we evolved to a more simple model with a 3D, we call it 3D onion, and then we evolved to a planar model with a stack of 20 layers. Each layer represents a bundle of nanotubes. Okay, now we will discuss how we model the simple model. Simple model is just a stack of 20 layers, and we will model the tensile test. So these are the clamp of the machine. This is half gauge length. The gauge length is the distance from the clamp. This is the clamp of the machine. We clamp from the diameter, this is the cross section, and we will pull. The hypothesis that there is perfect adhesion between clamp and the external part of the fiber, and 20 layers. Diameter is pretty realistic. We use planar model because it was the only one that allowed us to represent real length, because we are talking about 25 millimeter of length, over 10 micron of diameter. So it's pretty computationally, it's very complicated to model. So this is the shear stress that I told you just a few seconds ago. So it's not a Coulombian shear stress. So if I apply pressure, I will not obtain more shear stress. And the shear stress then have a plateau. Okay, this is the results of the simple model. Okay, simple model is the map of tension, axial stress in each layer. For 0.01 strain applied, 0.045, 0.2. So having a look on this cross section, we can see that even the stress in the external part is more higher than in the inner part. And in particular, we cannot obtain the uniform stress across the cross-section of the model. And this is not good because we cannot pull the material like a bulk material, like for example a sample of iron. So then we will obtain the uniform equilibrium of cross-section just very, very far from the clamps. We talk about 800 times the diameter. So this is, we show here near the clamp the axial stress. So this is external, internal. So there is a lot of spread. And then the spread just go down and then became more uniform. Okay, we made, after a parametric study about increasing gauge length and clamp length. I will show here the clamp length effect that is more important. So increasing the clamp length, so the length of the pullet of the clamp of the machine, from 0.2 millimeter to 20 millimeter, I will obtain better performance over the strain, And this is because if I increase the clamp length, I will pull better all the material inside my clamps. So there is very, very low shear stress between each layer. So if I don't pull a lot of fiber, I will not transmit the stress inside the fiber. I will not use all the material. This is the reason about this increasing of performance. Here we will have the distance from the clamp where the axial stress has equilibrated. So if I increase the clamp length, I will obtain the equilibrium sooner. If I don't have enough clamped length, I will not obtain any equilibrium. So I will not obtain, even in the half gauge length of the fiber, the equilibrium of stress. So longer the clamp, sooner the stress equilibrates along the fiber axis. Okay, we made another step. That model is very simple. We don't assume any impurity, but it's not like that. This is a microscopy image of a very impure fiber. It's very dirty. There are a lot of impurity cluster. We use this one just for cluster pickup. And this is a very clean fiber. And so usually established thinking is that removal impurity will be a good thing for mechanical property. But having a look on the experimental result, okay. Okay. It's not like that. So here, okay, it's not like that. Here we have the fiber containing impurity and the spoon fiber. So the fiber containing impurity are better performance. They have better performance. And okay, they are more reliable because there is better consistency in clean fiber, but not higher strength. This is we talked about these things and modeling the fiber. We approached trying to model this kind of impurity. So this is a sort of impurity that we can find inside. So swap, for example, like swap of bundle, entanglement, a sort of link between bundle, U-turn, and particle. Now we focus on two of the main impurities that are the polymeric coating and the particulate. Okay, this is a sort of glue that just coats the bundle and acts like an interface between two bundles. And of course, it will change the shear stress in a good way because 50 kilopascal of shear stress is very, very low. It's like a lubricant. This is a particulate. This is a sort of, when we catalyze the fiber, there is sort of ion particulate here. It's trapped inside. And this is a good thing. Because even if the density of material is getting lower, if we, what's happened here is that if I apply more pressure, I will not have more shear stress. But if I trap inside my clamp this particle, they will have an effect like sandpaper. So we can pull more material. So it's something good. And modeling this, increasing, so we model it, this is the standard model, and then we apply 10 times the shear stress inside the fiber. And having a look, here we have the equilibrium. Here the equilibrium is there, and here is there. So it's better. And the performance, the results are in accordance of this, of the map. So concluding, the stress distribution over the cross-section equilibrates with distance from the clamp. So we talk about 800 times the diameter. The longer is the clamp, the sooner the stress equilibrates along the fiber axis. The measurement of the tensile test depends on the clamp length. This is an important thing. So what is trying to say? It's trying to say that if I test my fiber in one laboratory with one test machine with 20, for example, 2 millimeters of clamp length, then I took this fiber and I test again in another machine with another clamp length, the result will be different. So this is important. And then we underline that network and higher friction help the transmission of stress, and removal of impurity is not necessarily an advantage for mechanical property of the fiber. If you are interested on the full paper, we just impressed on carbon, you can find the doyat in the conference proceeding. Thank you so much.